पेपर प्रेजेंट गर्ने हो कि स्लाइड बनाएर why we're not listening anything.
Yeah, I'm not sure what's going on. I'm trying to ask you this.
We cannot hear you. No.
Two authors of the paper are actual developers of Gaussian software, and they do have an idea what they were programming and what is included there. Okay, so let's plan our meeting. So we will have administrative part, planning our efforts for the remaining week, and then there will be a little scientific part summarizing the TDDFT in a form of a flowchart, as we did before, or other methods. And maybe I will add a little summary of the whole course. Okay. Oh, I was planning to bring another handout. It is not here. So we do not have any more homeworks, but we should invest our time in working on independent projects. And today I would like to make another lab. It is not obligatory. It is just a kind of office hours in the lab. So if anyone wants to talk more and get help regarding projects, I will be more than happy to be there from 6 to 9 p.m. So we are going to speak a little bit more about projects and what should be in the papers and presentations. But I would like to make a little disclaimer, a little announcement. So indeed, those independent research projects, written papers, and oral presentations are considered as volunteering, as a free will activity. If anyone is not happy, we can go standard way and make a standard exam, just answering questions, grading them, and which I don't know. So let me know by email or orally if this activity of making written papers and presentations is a substitute for an exam on a volunteer basis. Okay? I hope that you like it better.
And excuse me, Dr.
Yes.
Gillen. For project, what we have to do? We have to make slides and report as well, both of them, and how we.
Yes. So let me share the plans.
Okay.
So today in the lab and during this weekend we complete all calculations, and by Tuesday in class, every of us will bring printed version of the draft of the written report. It should be 2 pages, not very long, and it should be possible to write in a short time. Then we will discuss and refine it right here in class. And by Wednesday morning, I'm submitting Word files of your written reports to a publishing company, so that by Thursday morning we have printed versions of the booklets in class. Okay? The presentations will be on Thursday at this time, a week from now. And the time limits for presentations will be really short, 5 minutes, so that no one of us get bored. We will try to condense and be efficient, productive, and happy, so that we finish it quick. And it is a suggestion that presentations go really well if they are accompanied by movies, and probably while writing the written reports, there is no time to focus on movies. So after they are done, I will be waiting for everyone, or anyone who wants, in the arts and science basement, so that the very fine touch for project, there you have a chance to prepare a movie and insert it into the presentation. Does it make sense? Okay. So I think we are done with this little plan. So I'm announcing additional session today. And we are going to complete the academic part of the course in about 1 hour. And here I'm trying to refine the titles of the project according to your wishes, according to your selections. So if you see that something is not corresponding to your plans, let me know. I'm just wanting to keep track of what you guys are doing. Okay, let me mumble a little bit of general things. So what can be inserted into the written reports? So we all are busy. We do not have much time, so it should be short. So please try to make it 2 pages. There is no time to make more, and it should be a standard, fake, reduced form of academic paper, which is usually has 4 sections: introduction, method, results, and conclusions. Right? And there is a specific purpose for each section. So it is not required, but it is an expectation. So you may want to make each of them about half page. So in the introduction, sometimes people are saying why the model is interesting, maybe making 1 or 2 references. Do not make it heavy for you. Add 1 or 2 and do not go too far. Then one typically says what are the open problems. So why one wants to investigate it further, why the community is not yet happy with some material or some method. And then one can guess a hypothetical answer for this unknown question. So like I suppose that probably we suppose, usually in academic one puts in a third, one supposes there is an answer. And then the fourth component of introduction is how computation can help to support this or prove right or wrong for this hypothetical. And after one is done with intermediate sections, in the conclusions one is claiming that computed results do support or do not support the original posed question. Two other sections are the methods are usually done in order to help any reader to reproduce results. So it shouldn't be like very detailed procedure because the readership is not everyone. One expects that reader has a little background, but it should be enough details to help follow the steps and getting same results independently. You may write equation, or you may refer to software, telling which basis set you use, something like this, if it is a computation. And in the results, you just throw in anything you generate, figures, tables, and briefly explain what they are, and then share your vision why the results look this way. So to support that, the title is Results and Discussion. So this is a general thing, not part of this course, but I hope I didn't made you bored up to now. Okay. I was browsing through Wikipedia about this things about how to organize a paper, and found something. So usually discussion is a part of scientific paper, and questions about how to discuss subjects and how to organize presentations were of interest for the civilization, for human society for several thousand years. And they were even writing books about 3,000 years ago how to organize statements so that they are better perceived. And the only thing that we are interested now is how to organize our report. The rest, something is like how to speak it loud or not loud, and how to help audience to memorize what you are saying, but I think we do not care about it right now. Those, according to those ancient guys, 3,000 years ago, they were believing that the reason, that the tactical goal for delivering any speech or any written report has three components. I do not know how to read Latin. Docere, movere, delectare, which means teach, entertain, and motivate people to do something. So motivate, it relates more to court trials, like attorney wants judge to go to a specific decision, and teach is more academic, and also it is according to those ancient guys that any presentation should contain an entertaining component. I don't know whether it is truth or not. And one of those ancient theorists, Cicero or Cicero, I also don't know how to pronounce it. It was standard way how to organize paper, a presentation, several thousand years ago, and it had a little bit more complicated structure. So, and here are the Latin names for this part. So the first three are probably what we call introduction right now. So, why we should go forward, what actually are open subjects, and what is a statement that we want to support. Right? Then method and results are probably going to this part. So support confirmation of the of the main statement. And this part corresponds to discussion. We may want to expect that someone in the audience or in the community will not agree with the reported results or with the interpretation, and we should be ready to answer it. We should think ahead in a critical way about our own work and prepare some arguments in response. And the conclusion is a summation of everything that was found to claim that original statement was supported. And then there are some funny things. So blame anyone who disagrees and induce positive feelings toward the author. It's not my invention, it is this guy from ancient Rome. So it is a standard way to deliver a presentation, so you have an idea what to write in your written report. So I think Dr. Huang was presenting this little chart. So in case you do your research project based on, if you have an idea what to do, if it is related to your everyday research, you know much better what are your goals, what are the open questions, and how you are going to answer them. But if you are unsure and you want to do a little practical, little educational research, the simplest, maybe a little silly question is how the properties of material are perturbed by thermalization. What's the difference between electronic properties of a system at 0K, at absolute no motion, and when the structure has been perturbed by motion of ions induced by thermalization? And if we select this academic training part, we can arrange. You are already past this line, but if you are in the middle, one can arrange the computation in a way so that after selecting a model, optimize geometry and find electronic structure for 0K, then thermalize, and most interesting and unexpected, surprising results are expected at higher temperature. So instead of room temperature, you can try something like 1000 K or 2000 K, then you really will see some melting or explosion or decomposing of your substances. And it will be, I promise that it will be very visual if you do movies. How to break the model. And then you do electronic structure after you take the quant car, after the model has been decomposed. And it will be a big surprise to see what happens after heat treatment. So one of the expected things is that if the system does have a wide band gap after thermalization, the band gap disappears. One can test it. And then by comparing them, it will be enough for little educational project to Okay, I was showing this table a couple of weeks ago. So it is probably you are on a good track, you know what to do, but it is kind of support if you are in doubts. So just taking the model and recording different properties for different brands of the model with different configuration. Okay, so let's conclude the academic part. Done with administrative, organizational. Now let's talk a little bit more about time-dependent density functional theory. So, I will try to summarize what we did last time, give an example based on our practical session last Tuesday. Then establish flowchart to get an idea how the codes for time-dependent density functional theory are working. Okay, so it should be a summary. Summary of TDDFT. So through, oh, I'm scrolling back one sentence. Major surprise of playing with TDDFT, time-dependent density functional theory, is that the results, the computational data that are generated by this method are not time-dependent. So the actual results are in contrast with the name of the method. So the time dependence is only an auxiliary tool to develop the equation. And the outcome, the computed results of this methodology are transition frequencies and transition densities. So there is a set of excitation energies, transition energies, excitation energies, at which system feels comfortable to be excited. The goal of TDDFT is to find those energies at which system can be promoted higher up. And practical help, practical usefulness of this computation that based on these two things, this one is a little perturbation to total density. Perturbation to density. So based on this perturbation to density, one can find transition dipole moments, plug them into oscillator strengths, then oscillator strengths and the excitation energy are plugged into an equation for what? For an absorption spectrum, right? So this is enough for, so this little chart is enough to use time-dependent density functional theory in practical sense. You take your model that you processed before, you order TDDFT computation from the software, and you extract those oscillator strengths and build the spectrum. Then it is, maybe it is not always corresponding to experiment to like 7 digits precision, but qualitatively for single excitations, it is believed to give good understanding of the basic process. So a little example from our practical session. So in our lab last Tuesday, we were applying this TDDFT methodology to a little isolated molecule, the titanium plus ion coordinated to 4 hydroxyls. And practically, one takes the same input as for regular DFT, but adds a couple of lines to specify that it is time-dependent calculation. So the important thing is to include keyword PD, and also one need to specify how many excited states we want to treat. And we will see in a couple of, about 15 minutes, in a little bit more details why it is important. This parameter, this variable root, stands for number of excited states. So after we do all these things, one does analyze the .log file, and what we see there, there is a human verbal explanation that there is a list of excited state 1, excited state 2, excited 3, as many as we have specified by the root variable. So here it will be up to 20. And And if you do look on this little record, it shows several things. It does show the excitation energy. So this is omega sub 1 for first excitation. And for the second excitation, it will be H bar omega sub 2. And then there is a list of the remaining excitation frequency. And one can play and make a little experiment. Extract the energy difference between HOMO and LUMO orbitals from DFT calculation and look on this energy and observe that they are different. So the TDDFT methodology includes interaction of electrons and holes, and the energy of excitation is adjusted in respect to orbital energy difference. And it is the main benefit of using this theory. So another thing that one does have a notification of pairs of orbitals which are getting involved into the excitation. Involved in excitation. And what is interesting that there is only one pair for first excited state, but it can be 2 pairs or even 10, 100 pairs if you go to higher excited state. And in addition, the software right away provides the oscillator strength. This little record is F oscillator strength sub 1, F oscillator strength sub 2. And software builds columns of this data. Okay. I hope you were here when Dr. Huang presented this little matrix. Do you recognize it, or not quite? If not, I can happily repeat the background thing. But the basic mechanics of TDDFT is that in addition to occupation numbers that are present in regular ground state DFT, in regular ground state DFT, you have occupation numbers of orbitals, either which can be 1 or 0, orbital occupied, unoccupied. In the TDDFT, you replace this occupation of an orbital with a little bit more complicated construction with density metric that shows occupations on the diagonal. So this main diagonal would be occupation of the orbital HOMO minus 1, HOMO, which will be 1, LUMO, LUMO plus 1, which will be 0. And in addition, there are cross terms which show connection between different orbitals. And those connecting objects of diagonal parts of density matrix are getting non-zero when system is being perturbed by light. And all TDDFT methodology deals with these off-diagonal blocks. And here is a little illustration how the output of the software corresponds to this little chart. So we are coming from orbital HOMO to orbital LUMO, the first excitation, which means that this off-diagonal element of density matrix will be non-zero. And here it gives which value is assigned to this element. So as users, we do not need to think about matrices. We just see the pair of orbitals and relative weight of this transition. But if we would plan to ever rewrite the code for TDDFT, we may want to program a matrix and think about designing equations for populating all those elements, finding their values for each excited state. And for first excited state, the rest is 0. this is so it is an illustration of the output of the TDDFT. So we do have frequency, we have oscillator strength, and we have transition density matrix element. So for the second excitation, we have different simultaneously two pairs contributing to excitation. So this one is HOMO -1, this one is LUMO, and for the second pair, it's again HOMO -1 and LUMO +1, right? So let us draw arrows. So this one will be from HOMO -1 to LUMO, and this one will be from HOMO -1 to LUMO +1, right? So the output of the software prompts us that these two elements will be non-zero. This and this. Okay? So we are getting more and more comfortable with this approach. And here are transition energies and oscillator strength. Very good. So now we completely happy with practical side. Let's look a little bit more into background theory with very, very little so that we do not get tired or exhausted. Oh, okay, a little bit more things. So when we combine this oscillator strengths and transition energies, we are getting absorption spectrum. And it is presented here. And our little friends, our little first and second excitation are contributing to first couple of features here, but they are low intensity because we have seen that oscillator strength is really low for those excitations. And if you look for several others, they are getting more optically active. And actually, this number, the numbers here are in a relative agreement with expectations. So the titanium dioxide, which is formed by titanium 4+, has a band gap of a little about 3 eV. So there is no big discrepancy with this result. A little bit more above 3 eV. And here is the copy-paste of the keyword that one is adding into the input of the Gaussian software in order to get these numbers. Oh, okay. I was browsing through web page of the developer of this method. The name of, so we are going to look onto Casida Equation. And here is his web page. It looks like he is not too humble, and he tries to. He's in France, and he's trying to support his French background from the first word on his web page. So he's telling that yeah, it's primarily for French-speaking audience, but a little for English-speaking too. So here's the major paper that where he developed this equation. He puts a lot of photos of himself there. Just navigating through, I looked at his mother is a sculpturist, and he does some sculptures, and he is sitting in front of one of them. Okay, so here's the little summary that I was distributing last time. So let's, and actually it is based not on the Mark Casida, but based on some followers. So all equations here are extracted from this paper. So if you are bored, if you want to sleep, you can just take this paper and sleep for a couple of minutes. I would say no more in addition to what is taught here. So since it is time dependent, at least in name, one starts with time dependent Schrödinger equation, with the potential being considered as same nature as the effective potential in density functional theory. So it is pseudo world, not a real world, where multi-electron problems are projected onto single electron problems, and for each of those single electrons, one is solving equation which is similar to Schrödinger equation. But in ground state DFT, we were doing time-independent Schrödinger equation, and for perturbed time-dependent, one is starting from time-dependent Schrödinger equation. So the main idea is to take into account a little change in this potential introduced by external perturbation with a given frequency, right? This is what we were talking on Tuesday and what Dr. Huang was presenting 2 weeks ago. So as soon as we get a little change in the potential, we are getting a little change in the total density. And in the simplest, in the linear first order, this change to the total density is made to those strange connections between excited and non-excited states. So we do not have substantial change in the occupation of orbitals if the system is irradiated with very weak irradiation. We do have a little contributions to those connections between ground and excited. And they are connecting holes, occupied orbitals, and electrons, unoccupied. And in the community of, well, in some communities, one wants to add additional discrimination between occupied and unoccupied orbitals, and therefore they use beginning of the Latin alphabet for occupied and middle of the Latin alphabet for unoccupied. So it is AI, meaning that it is a connection between hole at orbital A and electron at orbital I. This is O particle. And what is what another convention that they're using is also that instead of electron, they like to write word particle, which is not a big surprise, but okay, electron is a particle. Maybe they're thinking about some other exotic systems when other particles are also being excited. So there are expansion coefficients. There are expansion coefficients that do connect this space distribution of orbitals and an increment in total density. For regular ground state DFT, those would be one index object, just occupations. Here, for perturbations by light, they do have two indices because we perturb two orbitals are involved. And the whole problem of the TDDFT is to find the proper frequencies and find proper expansion coefficient. One is trying to set up equations for those expansion coefficients. There are two of them, one for excitations and another for de-excitation. And just for convention, they are stored, they're used when uses the letter X capital for excitations and Y capital for de-excitation. There is another little thing that I hope Dr. Huang has introduced to you. So those matrices, actually those expansion coefficients, at the same time they are referred to as density metric. So density metric is actually a metric, right? Two indices. But for computational purpose, those matrices are stored in a form of a vector. Did you hear it before? No? Okay. So let me probably scroll to an empty page and illustrate it. So it is a little technical thing, but it is important. So those X density metrics is stored in form of a vector for easier computation, just for computational needs. So I'm going to focus only on a couple of elements near the homo lumo. So we can say that there is a X homo. Then next one on the diagonal will be X lumo, where X homo, where X lumo, Okay, so it is not the whole matrix. We have a lot of elements before and after, and it is a matrix. Right? So it is converted into a vector. So there is no transformation of the values. It is just a way to store the matrix. So it is rearranged in just row by row. So row by row. X, comma. The next will be X, comma, lumo, X, lumo, comma, X, lumo, comma, lumo. So the matrix is stored in a form of a vector. So there are same numbers, just arranged in a different way. And it is very beneficial for practical computation. Okay? So I'm going to scroll back to previous slide, which is very condensed and have all formulas from this paper. So those vectors for excitation and de-excitation are, one goes even further, they're combined in one big supervector, and this supervector is a density matrix in a vector form. Okay? And then one is designing an eigenvalue equation for those elements of density matrix and for frequency. So we typically play with eigenvalue equations for wave functions or orbitals. Here it is a different thing. It is the same type of equation, but for very different object. And therefore, instead of Hamiltonian, here this super matrix. And super matrix is not a word that I made up right now. It is a terminology. I'm not telling that it's super because it is impresses everyone. It is super matrix because it is some object that acts on other matrix. And by acting by this super matrix on the density matrix stored in a vector form, one is reproducing the same density matrix with an eigenvalue. So if you would have a couple of weeks more, we could try to derive equations for the elements of this super matrix in class. But I think you will not mind if you skip it for now. But it is the major equation. It is referred to as Casida equation. And it does allow to find the excitations, the frequencies at which system wants to be excited. So any system does allow only selected frequencies for excitation, right? It is why we see spectra, not continuous but several lines. So by solving this equation, one obtains set of frequencies and set of those transition density metrics. a little information, what is here, what are those elements, is stated below, without much details. So those A and B contributions to supermetric include two components. First component is the difference of ground state orbital energies. So energy of electron minus energy of hole. This is trivial. And in the simplest case, or we're not going to do it, but in simplest case, one can neglect all other terms, do TDDFT procedure, and get a trivial result to reproduce the spectrum that one is getting in the limit of ground state approximation. The same things that we are getting with VASP. So it is like zeros approximation to TDDFT. We get excitation as pairs of electrons and holes that do not interact. But additional terms to the supermatrix, they do correspond to interaction of electrons and holes. So basically, it is Coulomb exchange term that is entered in the total density, total energy functional. And in order to go back from total energy functional to those A and B coefficients, one need to take a couple of derivatives, a couple of functional derivatives of the total energy. And in this paper, they taken first derivative of the potential, and we know that potential is already a derivative, right? E was already a derivative over rho of total energy. And here we take a derivative in respect to this perturbation to the density. So those two terms, two contributions, are corresponding to interaction of electrons and holes. And the diagonal elements on A corresponds to, due to these delta functions, adjustment of energy of excitation. And off-diagonal elements correspond to possibility to convert of one exciton into another one. So one electron-hole pair can convert or can be delocalized over several to another electron-hole pair. But we do not need it for practical reasons. We have an idea what is in the code. Okay, we did this. And now we may want to go back to our standard way to understand software by setting up flowchart. So here's a dictionary to convert mathematical operations into pictures, into diagrams. So input, output, stream of data, mathematical operation, and branching conditions. And here is the summary of what we were discussing by now. So we are going to take these components and plug them into a flowchart. So we do start with the same input as for any computation, so positions of ions, number of electrons, some tolerance limit, because all those procedures are done with some given precision. And then in addition, one does need this keyword root, which stands for number of excited states that you do want to treat. As an output, we are getting the transition energies or frequencies. We get oscillator strengths, and we get this transition density matrix. Maybe they are not provided to us in form of matrices, but we understand that those information about pairs of orbitals, they are actually those transition density. Transition density. So the computation should include this Casida equation, right? Eigenvalue equation that will actually provide frequencies and transition density. And it should contain the connection between those transition density matrix elements and total density. Okay? Any objections, corrections, questions? You can compare what I show here with what is written here and say, no, 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 here you are wrong, or maybe not. Okay, so here's the little flowchart. You can do it together, or if you permit me, I will do it myself, just to save a little time. But we can, if anyone volunteers to populate, I'm more than happy. Okay, let me do it this time. So at the end, we are getting frequencies, and I add the curly brackets to support that there are many of those. Omega 1, omega 2, omega 3. We are getting oscillator strengths. And also I'm adding the curly brackets to show that there are a few of them. And in addition, if you are too curious, we can get information about pairs of orbitals that are stored in form of this transition density matrix. Which are also, there are many of those transition density matrices. For each specific excitation, you get a specific transition density metric, right? At the beginning, we need this root, number of excitations, and we have standard information, positions of ions. We use the same index. Just positions of ions. Tolerance limit and some electronic configuration, number of electrons, charge, multiplicity, the standard things. Okay, so we do need to combine three things: Casida equation, connection between density matrix and total density, and an equation to get the coefficients of the Casida equation out of total density. Coefficients for Casida equation of total energy, total energy and density. So in a very approximate way. So here is not a long, precise equation, just as a sketch. You say that those coefficients A and B are second derivatives of the total energy in respect to total density. But this is too vague. One needs to add more specific for actual computation. Then total density is ground state density plus summation of holes and electrons, those AI, which is specific for each excitation, times wave function orbital, one electron orbital for hole, orbital for an electron. Okay? So it is very similar to what we had in the ground state DFT, but with the only difference that our expansion coefficients do have two indices, and summation also runs over two indices. And here I'm going to practice my memory and reproduce the Casida equation. And I have something to look at if I forget. So those are diagonal things, those are off diagonal things, and they're not numbers, it is bigger matrices. And this to supermatrices. They act on this way, and they are providing the same x and y with a factor that is eigenfrequency. And there is a little thing that electrons are contributed with positive sign and holes are contributed with negative sign. Right? And as any eigenvalue equation, it has multiple solutions. So solving this equation, we get immediately all set. So here we should have a comparison with tolerance limit. And we are looking, we need to focus on a specific excited state. There are many of those, but well, now we do have parallel computing, but originally computation was just single thread, one thing at a time. So original algorithm focuses on one frequency at a time. We select some specific value of index for excited state, and we are comparing the frequency for this excited state on the previous iteration, omega old, and frequency of this excitation mu at this iteration. So in case we get consistency or energy of the excited state, we are going further. If consistency is not achieved, we repeat the same procedure. So we funnel those A and B coefficients into Casida equation and finding the transition densities over again, and transition frequencies over again, construct total density, find these coefficients, and repeat the whole procedure again until consistency is achieved. Then, if we are successful, we are looking if we considered as many excitations as the owner of the code desired. Because at the beginning we order specific number of excitations, and we typically order not too many of those because we want to save computational time. So this is number of excitations. If we achieve them, we just report the final result. If we didn't achieve it, we go to next. We just iterate next excited state, and here we start from I plus 1. So we go to next excitation and try to optimize it through this refinement cycle. And in comparison to ground state DFT, we repeat the self-consistent procedure as many times, as many excited states we need. So if you want 20 excited states, then your computation will run at least 20 times longer than ground state DFT. If you want 1,000, then same factor. And in case we are not picky about electron and hole interaction, we can neglect all this stuff and just make pairs of electron and hole orbitals. It is what we do with oscillator strengths in VASP. So we neglect electron-hole interaction, but for this approximation, we save a lot of computational time. Our computation goes 1,000 times quicker if you consider 1,000. Okay. So here is the same thing with computational symbols, just a little better than handwriting. And I think this lecture, this presentation is already on the D2L. If not, I will put it there, just in case if you need this right up. So, what have we done for last January, February, March, half of April, 2.5 months. So we considered molecular Hamiltonian, Born-Oppenheimer separation, the Hartree-Fock method, ground state, density functional theory, and our last thing was to get acquainted with time-dependent density functional theory, which actually doesn't have time dependence. And in our practical components, we made ourselves comfortable with building models, optimizing geometry, and finding some basic stuff like ionization energy, finding absorption spectra either by simplified method of orbital difference or as well as more reliable TDDFT that includes electron-hole interaction. And we also had a little section on learning how to do ab initio molecular dynamics and how to convert it into formal movies. I think we are in a good position to apply all the skills to real life, and I hope that you will be able to demonstrate your success in making these little practical things for the course, and later for all of your academic life, you'll find the skills useful. With this, I announce the end of the lecture and wonder if you want to ask something or discuss something or add some comments for the lecture. Is this you? Not now? Okay, so please, if you want, any of you is welcome to join us in the evening session in the Art and Science building today, and I'm looking forward to your 2-page reports on Tuesday. Okay, thank you. Class is dismissed.